Today we're going to look at the three-dimensional shape of molecules. Three-dimensionality of molecules is dependent upon electron pairs which repel bonds into a certain position. The key idea that I want you to keep in mind as we are going through this is that electron pairs want to be as far apart away from each other as possible, because negative repels negative. That's the key idea here. This is a lot more fun if we model. And I know I have fancy kits, but I'm going to use marshmallows instead. You need at least 6 toothpicks per group, 1 large marshmallow, and a minimum of 6 small marshmallows, but I recommend a few more because by the time we work down through that worksheet, the marshmallows don't look so good anymore. Come on up, help yourself to marshmallows and toothpicks. The big marshmallow is always going to be the atom that goes in the center of the molecule. Toothpicks represent 2 electrons. If the toothpick is placed in the large marshmallow and there's no marshmallows on the other side, this is called a lone pair of electrons. There are 2 electrons being shared here, or pardon me, there's 2 electrons on this end that are not being shared with another substance. For example, if we do the Lewis dot diagram for oxygen, do that on the board. We have 2 lone pairs of electrons. If there is a small marshmallow on the end of the toothpick, this represents 2 electrons being shared with another atom. We call this a bonding pair of electrons. Please begin by building a model with 1 central atom and 1 other atom attached by a single toothpick. You have a piece of paper that I left on your counter. In the first column, how many atoms are there in this molecule? 2. So, how many electron pairs are there around the center? 1. Just 1. We only have 1 toothpick. That represents 1 pair of electrons. Is this a lone pair of electrons, or is it a bonding pair of electrons? It's bonding because it's attached to another marshmallow. This means that these 2 electrons are being shared between these 2 atoms. There are no bonding pairs in this molecule. Please sketch this. I know. All you have to do . There is not going to be a bond angle reported because a bond angle is the angle between 2 bonds. There is not another toothpick to compare the bond angle to, so please put a line through that or an A. How would you describe the shape of this? Okay, What is the fancy mathy sciencey word for line? Linear. The name for this molecule shape is linear. L-I-N-E-A-R. In the next model, one large marshmallow, two small marshmallows, two pairs of bonding electrons. Your electron pairs must be as far away from each other as possible. Good. How many atoms are there in your model? There are 3. How many electron pairs? 2. There's toothpicks. Would you describe these as lone pairs or bonding pairs?
Why is it 3?
For the number of atoms? 1, 2, 3. It's the total number of atoms represented, okay? Are these toothpicks representing lone pairs or bonding pairs? They're bonding pairs only. There's no lone pairs. Sketch the molecule. What is the angle between this toothpick and this toothpick? 180 degrees. What do you think the name for this shape is going to be? It is also a linear molecule. In your next model, one large marshmallow, 3 small marshmallows, 3 bonding pairs of electrons. Go. Remember this central idea. Your electron pairs have to be as far away from each other as possible. Your electron pairs must be as far away from each other as possible.
Is the bond angle the largest angle or the smallest angle?
It will be the same bonding angles between each pair because this is not the correct model. Okay, look at the difference between... You lost an atom! Okay, look at the difference between my model and Calton's model. What do you notice?
They're equal distance apart.
Because here, is this the farthest these electron pairs can be? Oh, you want to make sure those electron pairs are as far apart from each other as possible. How many atoms in this model? 4. Number of electron pairs? 3. How many pairs are lone? None. They're all bonding pairs. Sketch. What is your bond angle between each one? Yes. Now you have to do a shape name. That's the first word. The second name comes from looking at it straight on. It's on, all the atoms are on the same plane, three-dimensionally. Trigonal planar.
I was close.
One large marshmallow, 4 small marshmallows, and 4 bonding pairs of electrons, please. Because you've forgotten the most important thing. The electron pairs have to be as far away from each other as possible. This is a 3-dimensional model and not a 2-dimensional model. So you've forgotten about all the space here. Oh, there you go. You're pretty close. Oh, no, don't move that marshmallow. You were so close with your structure.
Oh, it's triangle on the bottom. Yeah.
Now if I look out each bond angle, it should be approximately the same. Marshmallows aren't quite stale enough to hold the shape. Looks like a little bit like the Martian lander, doesn't it? Okay. What I'm trying to show here is that one's coming out and one's going back. Try as best as possible to do a 3-dimensional structure. We're not going to spend a whole lot of time on learning how to draw 3-dimensional. They can take care of that in organic chemistry if you go on. How many atoms do we have in our model? 5. Number of electron pairs? 1, 2, 3, 4. Are these lone pairs or bonding pairs? They're bonding pairs. Attempt to sketch. What is the bond angle? Guesstimates? Is it 120 like the last one? Oh. And it's not 90 because 90 would be this. So it's got to be somewhere between 90 and 120. 109.5. Oh, wow, you did this in Weyburn, didn't you? The bond angle is 109.5 degrees. If you imagined that each one of these creates a face, you would have 4 different faces, one on each side and one on the bottom. What is the prefix for 4? Tetra. This is a tetrahedral. Okay, same model, But if you take off one marshmallow,
So, for this, do you have to put 2 marshmallows on?
so 3 small marshmallows, 3 toothpicks that are connected. 1 toothpick does not have a marshmallow. It's basically the same as what you did the last time, but take one of those marshmallows off. This is a lone pair of electrons. This lone pair of electrons is not connected to another marshmallow. This means this lone pair is not being shared. This lone pair has only one job, and that's to repel other bonding pairs of electrons. And so what happens is it pushes just a little bit more than the tetrahedral model. And it forms this slightly different shape. Does it remind you of a particular 3-dimensional structure with 3 sides found in Egypt? Pyramidal. Oh. Okay, so let's go through the chart. You have 4 atoms. You have 4 pairs of electrons. 1 is a lone pair. 3 are bonding pairs. Attempt to sketch. The bond angle is 107 degrees. It's measuring the bond angle between bonds that are connected to another atom. It is not measuring the bond angle between here and here. This toothpick is not a bonding pair of electrons. They're lone electrons. So when you measure bond angles, it has to be between 2 toothpicks that are connected to other marshmallows. So again, the bond angle for this is 107 degrees. And the formal name is trigonal pyramidal. Trigonal pyramidal. Tri for 3, and then pyramid is kind of a shape, 3-dimensional shape. It's really easy to confuse trigonal planar versus trigonal pyramidal. Suggestions for keeping them straight. What is trigonal planar? That's right. So if you take a look at this upside down, so to speak, you'll see that the atoms are not all on the same level. So if it's planar and I look at it, all these marshmallows are at the same level. But if it's pyramidal, they're sticking up a little bit. They're not all on the same plane.
Does the lone bond count as an electron pair?
The lone pair counts as an electron pair. Yes. Start with this model and take off 1 small marshmallow. you should have one big marshmallow, two small marshmallows, 4 toothpicks. There are 3 atoms. There are 4 pairs of electrons. 2 of these are lone pairs because there's no marshmallow at the other side. 2 of these are bonding pair. Lone pairs of electrons only have one job, and that job is to repel. So these lone pairs push against these bonding pairs. There is a smaller bond angle between this one and this one because of the repulsion of these lone pairs. So it's not 107 degrees. It's actually about 104.5 degrees. How would you describe this shape if you were just to look at these marshmallows? What letter does it remind you of? V. So sometimes this is called a V shape, literally. Other times, depending on the author, you'll see the name angular. Either one is fine. Take off one more small marshmallow from this model. Oops, I just broke my bond pair. Need a new toothpick. You now have 2 atoms in the structure. You still have 4 pairs of electrons. 1, 2, 3, 4. 3 of these are lone pairs. 1 is a bonding pair. 3-dimensional shape. If you look just at the marshmallows, it's another linear molecule. Bond angle. You can't report a bond angle because there's only one angle. In order to report a bond angle, you must have at least 2 bonding pairs of electrons. Remember, these represent lone pairs of electrons. They are not connected. That means they're not forming a bond. There is another name for this shape that you might see. This can also be called a bent shape. Thank you for reminding me of that. It just depends what author they're reading from and what they were trained with, I guess. So here's how you use this chart of information. Whoop. If you take a look at the second side, at question 2A, you are given the name carbon tetrachloride. Do you remember how to do your Lewis dot diagrams? Oh, kind of, sort of. So carbon tet is CCl4. Which one goes in the middle? the C. The first one is usually your central atom. Do you remember how many dots that C gets? 4, because it's in group 4A. 1, 2, 3, 4. You have 4 chlorides. Do you remember how many dots chloride gets? 7. That's group 7A here. You start off by doing your Lewis dot diagram. Number 2, determine your central atom, which you've already said is the carbon. How many bonding pairs of electrons are connected to that central atom? 4. We have 1 bonding pair here, 2nd bonding pair here, 3rd bonding pair here, 4th bonding pair here. So we have 4 bonding pairs of electrons. Are there any lone pairs on carbon? No. There's lone pairs on chloride, but we're not worried about the lone pairs on the Cl. When it's asking you about bonding pairs or lone pairs, you're looking off of the central or the core atom. So there are 0 lone pairs. Then you have your table, which is on the first side. You need to find the molecule that has 4 bonding pairs and 0 lone pairs. The 3-dimensional shape of something with 4 bonding pairs and 0 lone pairs will be a tetrahedral. Carbon tetrachloride. Is going to look something like that. Let's try the next example. I'm going to erase the diagram. Your first step while I do that is to draw the Lewis dot structure of boron trihydride. Boron trihydride. Boron is in group 3A. It gets 3 valence electrons. Hydrogen is in group 1A. It gets 1 valence electron. Step 2, determine the central atom. The central atom is boron. How many bonding pairs are there around boron? So there's 3 bonding pairs. Are there any lone pairs? No. Use your table. and tell me what is the three-dimensional shape going to be? Trigonal planar. It's going to look like this. Questions? Try silicon disulfide on your own. You can also make a guesstimate. You know that electron pairs have to repel each other as far apart as possible. What the way it's drawn actually has these two double bonds as far away from each other as possible. This is actually going to be a linear molecule. We can't separate a double bond into two individual bonds. You actually have to treat that double bond as a unit. And so one unit or double bond has to repel the other double bond as far away as possible. Try C2H2, please. This is ethene, an alkene molecule. There's a double bond between two C's. It doesn't matter which carbon we make the central atom because it's a symmetrical molecule. For simplicity's sake, I'm going to say that this is the central atom here. Now there are four. Oh, that's a triple bond then. So then you are going to have one pair shared here, one pair shared here, and one pair shared like that. Kind of messy. Remember, the key idea behind this is that electron pairs are going to push each other as far apart as possible. So you have a triple bond between C's. What do you think is going to happen to this connection with the H? Yeah, because that bond is going to be pushed as far away from that triple bond as possible. So it goes, it can't be 90 degrees. That's not the farthest way you can push it. Go out to the side. And same thing with this connection between this C and H. You want that connection as far away from the triple bond as possible. What shape is that? It is a linear molecule. Sometimes the table isn't going to be perfect because you're going to have molecules that have triple or double bonds in there.
See, when you get me to come and sub for you, they ought to assign me to just sit here and be taught by you in the lessons preceding. Last class of today, do you have a class assigned?
At the end of the day, no, I have a prep.
So on this day, the 16th, the last class needs to be assigned?
Oh, yes, it does.
Because someone's been asking, and so I said, well, I think I might be available that period.
Yes.
So I am? Good.
Maybe let me know a little bit later.
It'll be Aaron.
Aaron? Okay.
Well, it'll be many. it's a group presentation they want done down.
Okay.
Grades 4, 5, 6.
All right. Sounds good.
Okay, thank you.
This is a linear shape, and this bond will be 180 degrees from this bond. Try E if you have not already done so. You have 3 pairs of electrons that are bonded, and you have 1 lone pair. This is not going to be a trigonal planar. The reason is those lone pair of electrons are going to push against the bonding pairs. This is when you're going to have that trigonal pyramidal shape. Here is what we're going to do with this in terms of assessment. You will have a table like this on your test. You have to be able to draw your Lewis dot diagram and figure out your number of bonding pairs and your lone pairs from the diagram that you've drawn. Then you need to use this table and be able to identify the shape of the molecule. I am not expecting you to memorize bonding angles. That's on the table that you have. Okay. Questions? Doesn't make sense. Tomorrow, we are going to look at how the distribution of electrons affects the way one molecule interacts with another molecule. So we'll be looking at what's called intramolecular and intermolecular forces.